Okay, let's get started. So our last class, we actually developed sort of the theory behind how we can actually get any point along our transmission line, how we can actually calculate what voltages and currents are going to be. But unless we're looking at specific fault conditions, that's not really all that helpful for us. What we'd like to do is just take a look at that transmission line and sort of block it as one big piece. And so in electrical engineering, we often use the concept of what's called a two-port parameter. You have an input port and an output port. And then what's inside the box can be a whole host of different things. And so what we're going to do is we're going to represent our transmission line inside the box. And then our two ports, we have a receiving end and we have our sending end. So those are the terms that we're going to be using, receiving end and sending end. Again, the receiving end is what you're trying to control to, meaning that's nominally what you're going to have for your voltage. So 345 kV would be VR. IR would be based on the load that would be expected to be there. And then the source end is just what it needs to be able to support what the customer is willing to pay for based on the system that you, the utility, has designed. So you've designed and built the transmission line, and if you do a bad job at it, then you're stuck with whatever the losses are. Now, that's not realistic because obviously it's a cost plus basis and we actually end up paying for it. But the idea is that they have to deal with whatever the transmission line configuration is. So that's what's going to be variable, both the voltage and the current. And if we do our two-port parameter, then we can just stuff it into a matrix. And so instead of having our transmission line with some inductors and resistors and capacitors, we can model that just by using matrix algebra and writing our two equations inside of our matrices, which just says Vs equals AVR plus BIR. And then IS equals CVR times DIR. And so what our job is to figure out what A, B, C, D need to be equal to be able to get these equations to calculate properly. So if we go back to our original equation with all those hyperbolic sines and cosines and gammas and characteristic impedances, if we use what's called the T equivalent model, and a T equivalent, I guess looks like the letter T. I don't really see it, but here is my, here's my admittance. That's Y. And then here is the impedance of the line. So I guess that looks like the letter T. I didn't coin that term, but that's what they did. And so if you use the T equivalent model, then you can just go ahead and very quickly calculate what A, B, C, and D need to be equal to. All right. So pretty simple, except nobody in industry uses the T equivalent. Everybody uses the pi equivalent. And the reason why they do that is because that capacitance is distributed along the entire length of the line. And so some of the benefits of the capacitor should be shared equally on each end, some on the receiving end and some on the sending end. And so if you notice what I did, I took my capacitor or my admittance and divvied it up on either side of the line impedance. Now, the problem with that, though, is that that does not match the original T equivalent that we have here, right? You can see that Y is to the left or on the sending end of the transmission line representation, where here it's on both sides. So what we need to do is we need to make the two circuits equivalent so that whatever we have at the sending end is going to match the results, whether using the T equivalent or the pi equivalent. So instead of calling them Z's and Y's, we do Z primes and Y primes. Okay? There's still admittances, there's still impedances, but there are prime matrix. And so now we have to go ahead and calculate what those terms need to be. But what we need to do is we need to make sure that these are equivalent. So I'm going to write a couple of equations. And can anybody guess as to what this first equation is or how I wrote that first equation? Any ideas?
The voltage of E prime element divided by
Yep.
and voltage drop or the Y prime two elements.
Yep. Yeah. So what electric analysis or what electric approach am I using to write that equation?
At the sum of current and going to equal field.
Very good.
That current law.
It's Kirchhoff's or Kirchhoff's current law, right? You can see that this current, right, minus this current is going to equal the receiving end current. So I didn't just create that equation from scratch. I actually use KCL to come up with a circuit analysis equation so I can start to write A, B, C, D parameters. Okay. So if I do a little bit of algebra, my first equation, Vs equals A times VR plus B times IR, right? So I just did KCL to come up with an equation that makes sense, right? It's got to be a valid physics-based equation, but I've got ahead and I figured out what to do with A and B. How do I go ahead and solve for IS? What circuit theorem did I apply here to get that to work? Any thoughts? Nobody? This is a little harder, but it's still KCL. I have a current right here, right? That's Vs. And does anybody have any issue that I'm multiplying it by y prime over 2? Should I be dividing by y prime over 2? Ohm's law is V equals IR.
That's the big.
Which an admittance is the inverse of Z. So technically it is Ohm's law. It's just already been inverted to get the admittance term. So that's the first term. What else? Well, I see that I have IR over here. And I see that I have another current, VR times Y prime over 2. So those two currents isn't that the current out of that node? So IS, the current into the node, is equal to this current, call it current 1, plus that current 2. So this is also a KCL, but at the first node. Okay. So now I do a little bit of algebra and I end up with something that multiplies VR. We'll call it C. And something that multiplies IR, which we will call it D. So now I can see that my A term is 1 plus Z prime Y prime over 2. My B term is equal to Z prime. My C term is equal to Y prime times 1 plus Z prime Y prime over 4. And my D term is 1 plus Z prime Y prime over 2. Let's sanity check and see if our work makes sense. What's one way you can just look at this page and see how I'm getting some pretty high confidence that my results are correct? Well, one of the things you probably all were taught as engineers in first year engineering, what was the one easy way you could check your works? Check your units, right? Did they teach you that in first year? Maybe even earlier. But let's see. Does a voltage equal a voltage plus a voltage? Well, what should the units be of 1 plus Z prime Y prime over 2? What should the units be? Should be a unitless quantity, right? Because if I multiply a unit by volts, I'm not going to get volts. So 1 has no unit. What are the units of Z prime? Ohms. What are the units of Y prime over 2? Moles, right? So ohms times moles is a unitless quantity. So that one checks out. What about B? Well, I know IR has the unit of amps and Z prime has the unit of ohms. And if you remember Ohm's law, ohms times amps equals volts. So that checks out that unit. How about over here? Well, just like we did over here, right? It's basically the same number, except we divide by 4. So we know that that's going to be a unitless quantity, but we are multiplying by volts, and we should be getting amps, right? So we can see that V divided by Z, or volts divided by ohms, should give me amps. Well, Y prime is 1 over the ohms. So I get amps there. And similarly, this is exactly the same. I get a unitless quantity there because IR is an amps and IS is an amp. So I should be feeling reasonably comfortable that I'm getting decent results just by doing a quick unit conversion check. You can also do the 2-port parameter approach. If you wanted to, and I'll just write this really quickly. Remember what we talked about for linear systems? If you can find any coefficient, a coefficient for any operating point, because it's a linear system that's always valid, how can I solve for A? Well, A equals VS divided by VR when IR equals 0, right? There's no B term. I mean, there is a B term, but it's multiplied by 0. So it's completely gone. So if I calculate the circuit, VS over VR when IR equals 0, then I can solve for A. IR equals 0 means under no load conditions. So what I end up with, Y prime over 2, Z prime, I should say VS, Y prime over 2, and that is VR. Can I use voltage divider? Because VS is also seen across those elements, which are in series with each other. So VR is it Y prime over 2? This is where it gets a little confusing. It's actually 2 over Y prime, right? Because for using a voltage divider, I have to use ohms divided by ohms. So I can't use Y prime over 2. I have to invert it and use 2 over Y prime. So that's the impedance of interest divided by Z prime plus 2 over V prime, and that equals VR. And if you do a little bit more algebra, you end up with what we calculated for ABC. So you can do KCL, the nodes, and do a little bit of algebra, or you can do the 2-port parameter and go ahead and do that. Yes, sir.
On the right side of that equation, shouldn't that be V sub X? Then the second V sub R,
On the right side of which equation?
the one you just wrote in red.
Oh, yes, that should be VS. Yep. Thank you. Yes. Yep. So you can do that 2-port parameters. Sometimes it's really nice because you can see the results. But how would you solve for B using our 2-port approach?
Whatever next to A.
Which is VS or VR? So how do you force VR to be equal to 0? Very good. So if I wanted to solve for B, and B is equal to, let's see, that is VS divided by IR when VR equals 0, all you need to do is short circuit, right? Oh, I don't know why I just skipped ahead. Sorry about that. And you put a short circuit, which means one of the Y primes over 2 is gone, right? So now all I have is VS across the Z prime, right? Which is what we expect to get over here. Okay, so you can do the same thing to solve for C and D for doing 2-port parameters, but either approach works. Okay, so we're close, right? We've got A, B, C, and D defined as a bunch of parameters that are Y and Z primes. We also looked at our T equivalent, And now we can relate the two. So we'll look at A, and we see that the hyperbolic cosine of gamma L is going to be equal to 1 plus z prime y prime over 2. So I'm going to do a little bit of math, and I'm going to end up with y prime over 2, because again, I'm trying to solve for y prime and z prime, or y prime over 2. That's going to be equal to hyperbolic cosine gamma L minus 1 over z sub c hyperbolic sine gamma L. And that's equal to 1 over z sub c tangent hyperbolic of gamma L over 2. Then I do the same thing for z prime, and I end up with that right there. So wait a minute, Paul. You said this was going to simplify things. Does this look like it's simplified? Not at all, right? This looks like I've got a lot more work. So why would I do the pi equivalent? Well, let's plug in some numbers. Let's look at some typical line lengths. And we'll go back to the original equations, which had z prime, which is z times sine hyperbolic gamma L over gamma L. And we'll do the same thing for y prime over 2 as equal to y over 2 hyperbolic tangent of YL over 2 divided by YL over 2. So I'm going to take those two, and I'm going to actually plug in some numbers. I'm going to plug in some, some typical lengths of lines and gammas, and I'm going to go with a short line, anything less than 50 miles. And when I plug in anything less than 50 miles, I can see that my hyperbolic sine gamma L over gamma L is 1 at an angle of 0, right? 0.998 at 0.02. Let's call that 1 at an angle of 0. And the same thing for the tangent term. That looks close enough to me to be 1 at an angle of 0. I go to 100 miles, and I can see that it still is pretty close to 1 at an angle of 0 for both numbers, right? I'm off by 0.007 and 0.004. Once I get to longer line lengths, now I'm getting off, by 3% or, 1.4%. So now that's too long. So if my line lengths are very long, then I've got to go ahead and do my hyperbolic sines and cosines and gammas. If I want to be able to accurately calculate what's happening on the sending end, then I've got to use those parameters. My z parameter, I have to go all the way back to the root. If the line isn't all that long, then instead of having this, well, that's equal to 1, and this is equal to 1. So for a medium length line, my z prime is just equal to z, and z is equal to my lowercase z times the line length. So the ohms per unit length times the length. I don't need any hyperbolic sines or cosines to solve for z in the two-port parameter pi equivalent. And the same thing for y. I don't have any hyperbolic tangent in there. That's gone out because it's approximately 1 at an angle of 0. And there's a modification a little bit for a short line, which is that the lines are so short that that admittance that we have at each end of the line contributes so little to the performance or the characteristic of the line that we can neglect it. So our pi equivalent model simply becomes z and y over 2. For the medium line, where z is lowercase z times L, and y over 2 is y L over 2. No hyperbolic sines and cos. If I use a short line, that's all I need. I don't need any admittance terms. Takes all the difficulty out of it, simplifies it dramatically. Okay? Now, if you want, and if you're capable, You can always use the long line model because that's the most accurate. So if you want really high precision, you're more than welcome to use the long line model. But I will tell you in industry, it's pretty rare that you're going to get characteristic impedances. It's very rare you're going to get lowercase z and lowercase y. I've done a bunch of transmission line modeling, and even for longer lines, although I've done all my work has pretty much been done on the East Coast, and the lines tend to be pretty short. Every system that I've had, we've always used a medium length line. Even if it's a short model or a short line, you would use the medium line model. So the suggestion is, unless you need real high accuracy, then go ahead and use the medium line parameters. If you aren't given y/2 as a value, then go ahead and use the short line model. Okay? That's typically what you would see in industry. All right, this is a really busy figure, but don't worry about it. I put a lot of information here, and I've got a MATLAB script file that kind of works this one out. So we have a 345 kV, three-phase, 130 kilometer transmission line. So start thinking about what parameters you want to use. You have R equals 0.036 ohms per kilometer. Inductance is 0.8 millihenry per kilometer. And capacitance is 11.2 nanofarads per kilometer. So all of a sudden, you should start thinking like, wow, I'm actually getting L's and C's. I'm not getting any X of L's or X of C values. So one of the things you're going to need to do is calculate reactance, right? Because I can't do anything with this from an AC circuits perspective unless I have reactance terms. So I've got L and C. I'm going to have to go ahead and calculate X of L and X of C. I also tell you what the load is, and I tell you what the nominal operating voltage of this line is supposed to be, 325 kV. So I want you to solve for the sending end voltage, the sending end power, and then draw the phasor diagram. And then we'll talk about the phasor diagram in a little bit. All right, does everybody understand what the question is asking? You want to see basically what does the sending end voltage and power need to be able to feed that 270 MVA at a 0.8 lagging power factor load, given the line parameters that are specified. All right? Everybody understand what's being asked? Okay, so the first thing is we're going to find big R, big L, and big X, right? We need to find out what those parameters need to be in terms of actual ohms and not ohms per mile or henries per mile. So we know that we live in 60 hertz land, so our frequency is 377 radians per second, our radian frequency. So omega times L times the line length gives me a reactance. So this is the series portion of the reactance of 39.2 ohms for the entire length of the line. Now I'm going to go ahead and solve for the X of C. Okay, so this is the X of C equivalent for that line. And plug that in 1 over omega C, and I end up with 1820 ohms. My resistance is easy because there's no frequency component. So I just multiply the ohms per unit length times the length, and I end up with 4.68. So my total impedance Z is equal to 4.68 plus J39. And my Y/2, not my Y, but my Y/2 is 0.274 millimoles. Okay, not ohms, but moles. And notice I calculated Y/2 and not Y because I need Y/2. So I can just divide it out right then and there. So now I'm going to solve for my ABCD parameters with the fact that this meets the criteria for a medium length line. So A and D are the same. It's 1 plus ZY/2. And I end up with 0.98924 plus J, that small number there. My B is equal to Z, so that's pretty simple. And my last term that I'm going to calculate is my C, which you can see is a pretty small number. So this is be careful when you do these homework assignments, because your values of A and C can be pretty small. doing it on a piece of paper can be difficult. What I mean by that is it can make it so that it's hard to get good results because, 35.251 micro, if you just make that 35, then you might not get super accurate results. So just be careful about watching or keeping track of that. That's why I like to use it in MATLAB. I'll just specify what those parameters are in MATLAB, and then it keeps track internally. Now I got to solve for the current, which means I got to do the S equals VI conjugate. And it either has to be 3 or the square root of 3. So that's going to be 3 or the square root of 3, depending on which voltage I specify. Okay, is it a line voltage or a phase voltage? So I'm going to go ahead and draw my power triangle. And I'm getting given S as 270 MVA. I've been giving the angle between P and S because I know what the power factor is. And SOHCAHTOA tells me what that angle is going to be. So then I can just use my trig identities to calculate P and Q. So now I know what P and Q is. So I can actually write, an equation for I as my IR is going to be equal to 270 MVA at an angle of inverse cosine of 0.8 or the 36.87. Notice the angle is negative because I want this to be a lagging power factor. So I need to specify the negative there. And then I divide by the line voltage, which means I need the square root of 3 there. So my receiving end current, what is delivered to the load, is almost 480 amps at an angle of minus 36.87. Now I just plug that into my ABCD parameters. And again, this is why it's really useful to use MATLAB, because you have all the variables specified here. And I can do my calculations. Does anybody have any issues with how I entered in my matrices? There's something very sneaky subtle in there that I don't know if you see. So I will highlight to you. What voltage is that?
187.64.
Yep. What voltage is that though? Is that VR? Because the ABCD parameters, you have to set it up with that equation right there, right? So it should be VR. Is it VR in this problem? Is it 325 kV?
Yeah.
Everybody agree with him? I agree with him that it's not 325 kV, but it is VR. Anybody have their calculator handy? 325 divided by the square root of 3 is equal to, what do you think?
I'm going to guess on for these.
Good guess. Why did I divide by the square root of 3? Because this is a single phase equivalent representation of the transmission line. So I can't put in 345 or 325 kV there because that would not be across a single phase. That would be across two phases. So I need to, and this is a highlight in your notes. This is super duper important. Make sure you divide your voltage by the square root of 3. That is essential that you do that. If you don't do it, you're not going to get good results. Then when I do that, so last thing is, I also pick my reference voltage to be at an angle of 0, right? Because it's reference, so I stuck it at 0. So that's why you see an angle of 0 kV. So the magnitude of the voltage is because I divided by the square root of 3. The 325, I divide by the square root of 3. The angle of 0 is because that's my reference. And then when I calculate it out, that's my voltage and my current. Now, interestingly enough, the current at the receiving end is less than, the current at the sending end is less than the current at the receiving end. Any guesses as to why? Because the line has such light loading that, those capacitors on each end of the line are actually providing reactive power support, which means less has to come from the sending end than what is being delivered to the receiving end. There's actually reactive power coming from those capacitors. So remember the last class we talked about surge impedance loading? This would be a case that the power demanded is less than the surge impedance loading. This line is generating bars. It's lightly loaded. And how can I tell that? Well, it's a little bit hard to tell, but you can't tell too much about this system here. But I can look a little bit in terms of what's happening. So, and real world transmission line planners look at this all the time. They pick their reference voltage as a fixed value. So it's at 0 volts. And then if VS is a positive theta over there, that means real power is moving from the sending end to the receiving end. Okay. So just by looking at the phase angle difference between the receiving end and the sending end, I can tell you a power flow or estimate what the power flow would be. And why is that important? Because with a transmission line, power can flow in all, it's bidirectional, it doesn't care. So I can actually tell you if power is flowing from Orrington to Windsor, or is it flowing from Windsor to, over to Orrington. And I can tell just by looking at the angle. I can also tell which way reactive power is flowing by the magnitude, right? I see that the magnitude of VS is greater than VR. So that means reactive power flow is also flowing from the sending end to the receiving end. Okay? So I can look at this, and that's why I said beginning of the semester, I said knowing magnitudes and angles is really important because I can pretty well predict where power flows are going to be just drawing these phasor diagrams. The currents don't matter all that much, other than to say they're both lagging power factors. Most of the time when you look at current of the utility system, they really only care about the magnitudes and nothing else. Okay? Even though the transmission line is providing reactive power support, it's not providing all of the reactive power. You can see on the bottom that the sending end still has to pump in 162 megavars of reactive power. So if it was 0, then you would see that the magnitudes would be the same. But because you still need 162 megavars to go from the sending end to the receiving end, then that means that that magnitude has to be good. Okay. Here is, where is it? Where is it? Oh, where did it go? Oh, here it is right here. Here is that problem, right? All laid out for you. And I've just done it with a MATLAB script file. Again, I don't expect you to do it, but I like doing the script files because everything here keeps me honest, right? There's no hanky-panky. You can actually see the work. I can even do the clear CLC. So I'll do clear. So now there's nothing in the workspace for variables. So I'm going to run this. And toggle over to MATLAB. And then this tells me, oh, this tells me the value that I have. Okay. So let's see. So here's the upfront information. Here's the impedance data that we calculated. Here is the power. And then you can see I calculated my ABCD parameters. And then I just displayed a bunch of information. That's what this plot shows. Okay. I'm actually plotting VS versus IS. So I'm doing a plot of VS and IS. And you can see a slightly positive angle there in the IS. This is not great because everything is on, it has to be the same scale. So like the voltage is like 300 and I don't know, what is the voltage equal to when you multiply by square root of 3? The voltage is, oops, why is it saying 345? Give me 1 second. Oh, I got to run it over here. That's why. That's for a different part. So I'm going to run it right to here. Okay. And now we'll look at that. And that's the value that we have, right? So our sending end is 124-ish megabars, which if you look at the slides, I said 162 versus 124. Huh. Did it not display Q send? I'm not sure why that's off a little bit. Let me just double check. That's 3V times I. Yeah, there may be a typo in the notes because this is 270. Excuse me, this is the power factor. I is equal to the conjugate here. Yeah, so maybe I have a typo in the notes because this is, it looks like it's slightly less than the 162. But the angle, I believe, is right because the angle I said here was 25.57 and the angle over here is negative 25.66. So that's just a precision thing, right? Just being able to enter in a level of precision. So that's how you calculate it by hand. But a couple of key steps. Notice right here. It's not clicking on, sorry. Right here, I've got the square root of 3. So I entered the voltage in, the receiving end voltage, as an actual phase voltage. That's all I did was divide it by the square root of 3. And I ended up there. That's why I even put in the notes here, I said highlight, right? Notice the square root of 3. That's the most common mistake students make when they do this. They forget to divide by the square root. Okay? Any questions on how to do that? Sort of clear? All right. Whoops, what happened here? So what about unity power factor? So unity power factor is, no, it doesn't want to do it again. So a unity power factor, which means that the load is at unity, you can see that BS has a higher angle than VR. So I'm still moving power. Unity power factor means all of the load is all real power, but there's no reactive power there. So you can see that the magnitudes are pretty close to the same, but the angle is still positive. Then if I was to shift to a leading power factor, what does a leading power factor mean? It means at the receiving end, I've got a lot of bars that I don't need. I'm actually dumping those back into the system. So look what happens to my magnitude. My magnitude drops by a fair amount. So again, my system operators will be sitting there looking at VS magnitudes, VRs, and angles, and they'll be able to tell you where's power flow. And if the angles are really big, then you've got problems. If the magnitudes are really big, you've got problems. So just looking at these relative terms, then you can determine, all right, is the system going to fail or not? Generally speaking, magnitude should be no more than about a 10% difference, and angles no more than about 30 degrees. Okay? Once you start exceeding 30 degrees, you're really pushing the line operation. And the last assumption here, the X over R ratio of the transmission system, it generally is pretty high. So get it greater than 25 is usually a pretty safe assumption. All right, I'll give you 5 minutes and then we'll do this problem. You do the same thing. but do it on your own. Let's see if you can get it. I tried to make it a little easier. Give it about quarter past. So I've already told you the load, so I'll give you a hint. Look at the load. But this one, I'm switching it around, right? I'm tricking you a little bit. So now the sending end voltage has been measured at 345, and the current has been measured at 400 at an angle, whatever the angle associated with it is 0.95. So this is our receiving end, that is sending end. So you have to be mindful that you're not calculating VR and IR, you're calculating VS and IS as your terms. So you can still do the ABCD parameters, you just have to invert the matrix. Essentially what I'm saying is the power has reverse directions. So what normally is my sending end, now for some reason, the power flows have switched directions. Maybe, you know, if we're in Maine here, maybe New Brunswick, they had a problem in New Brunswick and they opened up the 345 kV tie lines. So all that power that used to come in through New Brunswick and then head down south now has to go in the opposite direction. Now we need backfeeding power to go that way. Or maybe you're in New York. There's a bunch of interconnection lines between New York and New England. So maybe depending on circumstances in New York, they are sending power back to New England. If you remember when we looked at ISO New England, they did mention, you know, there was flow and they actually reported the intertie flow between the two. So you can see that. So sometimes the sending end is actually what's being controlled. So that's what we're looking at here. All right, one more minute. You don't have to get the answer right, just kind of understanding the process a little bit. All right. Let's show you how I would tackle this. I love to draw pictures. Not much of an artist, but I like to draw pictures. Oop, don't know why that just did that. It really frustrates me when this does it, but. So I'm going to draw my equivalent circuit. Here's my VR and my IR. And my VS, I actually know what it is. It's 345 kV divided by the square root of 3 at an angle of 0. Remember how we need to convert those to phase quantities? So I'm going to divide my voltage there. My sending end current is 400 at an angle of inverse cosine negative 0.95. Now I'm going to solve for A, B, C, and D. And in my equation, I know what IS and VS are equal to. I know what A, B, C, D are equal to. I'm now going to solve for VR and IR, which are unknown, by taking my A, B, C, D matrix and inverting it, and then multiplying that by VR and IR. Okay. So these problems aren't particularly difficult. They're just, you got to be meticulous about which way you're doing things. So let's see if I have a MATLAB script file so we can take a look at our work. All right, so there's our voltage, our sending end voltage, our Z and our Y, and then we just converted Y to Y over 2 by dividing by 2. Our magnitude of our current is 400. Then I slapped on the angle, and I kind of spelled that out with a little more detail so you can see it. Then I calculated my ABCD parameters. Then I just defined a matrix called receive. And you can call it whatever you want. I don't have a preference. Then I pulled out my VR and my IR. And then I just make a display so that you can actually see magnitude and angle. And then I'm going to go ahead and do it. So let's go ahead and run this and see what we get for answers. So our receiving end voltage is just under 345. And this is the problem with using the display. You can see the angle basically says 0. That's because it's 345,000 volts. So if you want to make this a little bit easier to display, if you take display underscore VR and divide by 1 mega, it's still not showing the angle. So the angle looks very small. But my current is 400 at an angle of 18. So if I look at my phasor diagram, you basically have very little current shown there, and you have almost no magnitude angle difference between the two. So there's hardly any reactive power flowing from one side to the other, but there is some real power. So you can see here my receiving end power is 227 megawatts. So that's what the power is going into the receiving end. And my reactive power is only about 75 or 0.745. So about an order of magnitude less than the real power. Okay. And that's how you tackle these problems. Yes, sir. Yeah.
So you're.
Oh, yeah. Sorry. My S's are a struggle today. Sorry about that. Thank you. BS and IS. But again, the reason why you have to calculate it both ways is sometimes your receiving end is your sending end, and sometimes your sending end is receiving end. It really just depends on how the grid is operating. And the electrons don't care. They'll flow whichever way they want to. You may want them to flow, like you probably don't want electrons to flow from Orrington up to New Brunswick, mainly because they might not be paying for that power. They might not agree to buy power from New England. So they're running at a really low value and they're getting power for free. And there are ways to control that automatically. But the concept is there are some cases when you never want power to flow in the reverse direction. But in AC world, you don't have any control over that. In DC you do, but in AC you don't. Okay, everybody understand kind of how to tackle these problems? They're not hard, they're pretty simple. And I actually give you a problem, a real world example of the Orrington to Cooper's Mills line. So I'm giving you real world impedance data. I'm made up some loads, and you're going to tell me, essentially these parameters based on what's happening for that line, that 345 kV line that goes from Orrington to Cooper's Mills. So as I talked about, Orrington is just outside of Brewer. You're familiar with the area at all. Cooper's Mills, anybody know where Cooper's Mill is? Windsor, Maine. Anybody know Windsor, Maine? Augusta, Maine? You don't have to be specific, but Augusta, Maine is kind of in the middle. If you've driven, which most of you have, if you've driven either to Orono or the southern part of the state, you most likely will have driven through Augusta, Maine, just because that's the 95 and that's like the best way to get back and forth to Bangor. So it's about 10 or so miles outside of Augusta. And that's one of the 345 kV lines that heads out of Orrington. One goes to Cooper's Mill and one goes to Palermo. The information we have is on the one that goes to Cooper's Mill. So easy peasy with short transmission lines, we don't even have a Y over 2. So then our S is just going to be the voltage drop across Z, right? Just like we did with our very first homework assignment when it was V1 minus V2 divided by Z. It's the same concept here. So we get our current by getting the voltage drop, and then we get our power from bus 1 to 2 by multiplying by the voltage at bus 1. And then we do a little bit of modification, and what we see is S1 to 2 is magnitude V1 squared divided magnitude of Z, theta Z, minus V1 V2 over the magnitude of Z, theta Z plus theta 1, 2. So what about for a lossless line? So if we plug in for a lossless line, now we know that the theta Z, right? That's the theta 1, 2. What's the angle if it's a lossless line? 90 degrees, right? Because there's no R value. So if I take the inverse cosine of, or inverse tan of something that is, it's X over 0, you're going to get infinity. So that becomes 90 degrees. And so what we see is our power transfer easily can be determined by VI or V1 V2, magnitude only, divided by the X value, so the reactance of the line, times the angular difference of the line. So I can tell you how much max power I'm going to get based on letting the sine go to 1, right? Sine of theta 1, 2. If I go to 1, that's max power. So remember how I said the angle can never go to 30 degrees? Theoretically, you could get to 90 degrees, but that's right at what we call the margin of stability. So you would never operate it, but you can operate transmission lines at a higher value than what they're normally operated at. And that's how you determine it there. So you are always trying to get your reactance value low because you can move more power through the line. So dropping that reactance value, that series reactance value, is generally a good thing. Any ideas how you can drop the reactance value? It's an inductor. What cancels out an inductor? Yeah. Put a shunt capacitor. Not a shunt capacitor, a series capacitor. So in Orrington, there are series capacitors. That picture right there is of the Orrington substation. That's just a Google Maps picture. And those three, I don't want to call them boxes, but structures, those are 3 series capacitors. And the whole purpose of it is not to improve the reactive power of the line. It's actually to improve the power flow through the line. So those work really well. And both lines coming out of Orrington have static series compensators for it. We already talked about some of the max power stuff. Obviously, there's only so many things you can do for thermal. If it's too hot and it sags too much, you're out of luck. So there's really nothing you can do thermally once the line has been erected. The angular limits, we already talked about getting nowhere near 90 degrees. So 30 degrees typically, maybe 40 if you're really pushing a line. But that's the angle limit or the stability limit that you get. We have voltage stability, which means our voltage gets to the point it's so low, they call it a nose curve. And the reason why they call it a nose curve is as you increase the power, the reactive power, so this is Q and this is V, my voltage starts to drop until it drops so much that it collapses. Because remember, a lot of the voltage that you get is because of capacitors on the line. So your V squared over X sub C drops, not only because of the fact that you're pulling a lot of power, but the voltage, right? The V squared gets smaller and smaller and smaller until you get a collapsing point. And that's why they call it a nose curve. I guess it looks like a nose. And then the transient stability is basically if we have a fault on one side of the line, that system has to be able to respond quickly. So we already talked about series capacitors. That helps you improve power flow. Sometimes at night, you have too much voltage. The system is too hot. So you actually have shunt inductors, and Orrington does have some shunt inductors there. And if you get fancy, you could do what are called FACS, flexible AC transmission systems. And those are just basically nonlinear devices that either inject or remove reactive power. So in Chester, which is about 40 miles from here, they have a static VAR compensator that adjusts its output to improve the flow of the transmission line. And I think this Chester static VAR compensator is 40 MVA rated maximum, but it actually improved the performance of the line. So it actually pushes more than additional 200 megawatts on those lines just by adding those static VAR compensators. So for a 40 MVA static VAR compensator, you get a lot of bang for your buck. They have more sophisticated devices, but these devices are very expensive and can really complicate the operation. So sometimes better does not include a lot of complexity. You can make the system better by adding all these widgets and bells and whistles, but it doesn't always necessitate. So it doesn't always improve the system. So you do see a limited amount of flexible AC transmission systems where they incorporate that. And like I said, you actually have capacitors in series with the line. So these are located at a substation and not out in the middle of the transmission line, primarily because you have to bypass them. If you look at a one-line diagram, so here is my resistor and my inductor of the transmission line. Then over here, you have the series compensator, and that series capacitor that's only exists there. And then across it, you have a bypass switch where you can completely bypass the series compensator. So if it's got a problem, you can short circuit it out, and then you can open it up and do maintenance. Because you never want to have a system out there that takes your whole system down. A failed capacitor is not that uncommon. So if you have a failed capacitor, don't take out 1,000 megawatts of power supply. Go ahead and short it out, open it up, and then you can continue to operate. Oop. Be careful though, when you have series compensation, because the concept of resonance or resonant frequency, which is basically the magnetic energy and the electric field energy will ping pong back and forth. And you can just share energy back and forth where you can get some pretty high voltages and oscillations on your system. So that's why you have to be very careful about making sure your system is tuned, because 60 hertz is just a communications signal, right? It's big power communications, but it's still a thing. So you have to be very, very careful about just throwing things on there willy-nilly. There's things to consider. Yes, sir. A shunt capacitor usually just boosts voltage. So you'd put a shunt capacitor anywhere in the system because you think you're going to have bad voltage there. It doesn't improve the amount of power directly. What it does is it says, hey, I can run more current through the line because the receiving end now gets some local reactive power support. So I can push more power through the line because hopefully my magnitude of current increases. But over here, I've reduced the effective value of X. So I'm not even getting a lot of reactive power for a series cap. It's just that that value of X has dropped. So my V1 times V2 over X value goes higher. Okay. But yeah, shunt ones usually just increase the capacity of the line because your magnitude of current can be, your magnitude of current can have more real power associated with it. Okay, any questions? Because you should be able to do enough. You should have enough information to do the real world power system problem without too much effort. Any questions? Because we will tackle on Thursday, we're going to start getting into load flow, which is, if you've had Calc 3 and it's been a minute, you may want to look back at solving partial derivatives. I don't know, in ECE, they do partial derivatives all the time in EMAGs. That's pretty much the only class, right? You do partial derivatives. Yeah, I don't think many majors do a lot of partial derivatives. Maybe they do in mechanical, but we'll have to do some partial derivatives. So we'll do a review, a little bit of partial derivatives, because we're looking at sensitivities, and we'll go from there. Any questions? TV land or not? All right, well, no questions. Have a wonderful day. Oh, wait a minute before you all leave. I forgot to mention this. Please, if you have the time, I cannot encourage you to go to this tonight. They have 2 nights, tonight and tomorrow night from 5 to 7. You get to meet a company who's going to be at the job fair looking to hire engineers who work in this field. I encourage everybody just to show up if you have the time. First off, you get some free food, right? Which is never a bad thing if you're a college student. The other thing, which is probably even better, is you're actually going to meet some industry folks, and you can talk about the industry and then find out a little bit more about what's happening. They're looking for interns and entry-level engineers. And they're looking mostly for the utility one, but they do a lot of projects for Bath Iron Works and all that stuff. So you actually might have other opportunities that may be worth doing it. But that's SGC Engineering. They have an office in Bangor, one in Augusta, and one in just outside of South Portland. You know, is it an actual office or is it somebody's house?
Oh, yeah.
Okay, so they do have one in Presque Isle too, but I thought that was like 2 guys, but yeah, so there. But highly encourage one of your classmates, maybe they're trying to hawk the company a little bit, but highly, highly encourage you to go, because it is a really good company with some really good people.
Yep.
All right, y'all, have a great day.
Well,
Thank you.
and